Hey, welcome back to one more short video. So this one's going to be on an inelastic collision. So what we're going to do is we're going to have two asteroids that smash together and then stick together in the same spot. And what we're interested in discovering is given two initial momenta for these asteroids, these two bodies that are going to collide and stick together. Given their two initial momenta, what's the final momentum? And then importantly, what's the final speed? What's the final speed? How quick is it going at the end? Okay. I think this one will take a little bit less time than last time, so let's hop into it. So, just to make things, graphical, I've got two bodies. Mass one, call it asteroid one, and another body. Let's make it light blue. Let's go. Here's mass two, another body. Now they each have their own momentum vectors, p1 and p2. I'm interested in what happens when they hit each other and stick together. So if they stick together, it's called an inelastic collision. Inelastic means like they don't bounce off of each other. Elastic basically means they bounce off each other. So I call this a perfectly inelastic collision because they hit and just stick. And kind of like mentally summing up those momenta, probably in a point like that, say. So, yeah. Okay. So, and this would be like a total momentum here. So, what I'm going to do is I'm going to set up some, let's do numbers. So we'll say that momentum 1, or not momentum 1, mass 1, mass of the first asteroid, we'll call it 500 kilograms. And asteroid 2, it kind of looks bigger, so let's call it 1500 kilograms. Let's say it's 3 times as big. Okay, so let's also find some angles. So we'll say this angle here, I'm going to call this angle 50 degrees. And I'm going to call this angle here, let's call it 65 degrees. Okay, so we've got our problem set up. I've got, almost, we need one more thing. So I need initial velocity. So let's say that the velocity of the first mass, just the magnitude of it, sorry, the speed of the first mass is, I don't know, let's say 10 meters per second. Nothing too crazy. RIP, second technical difficulty. The speed of the second mass, we'll call it 12 meters per second. Okay, so I can already tell you my initial drawing was a little bit off. So P2 is going to be much bigger than P1. Let's go ahead and calculate that out just so I can show that the magnitudes are going to be bigger for 2 than 1. So the magnitude of P1 is just going to be M1 times the magnitude of V1, which is 5,000 kilogram meters per second. Meanwhile, the momentum of 2, the magnitude of the momentum of 2, is just going to be the mass of the second one times the velocity, the speed, sorry, of the second one, which is 12 times 1500. So that's going to be 18,000 kilogram meters per second. Okay, cool. So let's codify my question. My question is, what is the magnitude and direction of velocity for the joined masses after collision? Can I spell collision? 2 L's, 1 S. There we go. How does this compare to previous velocities? All right, sweet. Okay, let's do it. So what I'm going to do now is I am going to just add up these momenta. So we're just going to decompose these vectors, these momentum vectors, into their parts, add them up, and then momentum must be conserved for this system. So yeah, it should be pretty much just that simple. I do want to say, motivate that last statement a little bit. So I say that this is a closed system. There's no external force acting on it. That's to say that these two asteroids are like far enough from other asteroids, from other bodies, that that they don't interact with those other ones. There's no external forces. So that's the reason that I can say that overall the momentum, the total momentum of the system is conserved. There's no change in the total momentum. Okay, so let's go ahead and just decompose these vectors. So P1 first, let's look at the general direction. It's pointing to the right and up, so I expect both values of the momentum vector to be positive numbers. I'm measuring my angle relative to the horizontal axis, so I'm safe to just go ahead and apply cosine of the angle, and it's a 50-degree angle. So the x component is going to be the magnitude, P1, the magnitude of the thing, times cosine of 50 degrees. And the y component is going to be the magnitude of P1 times the sine of 50 degrees. All right? And I'll just go ahead and write that in. So P1 is 5,000, 5,000. So the results are going to be 3,213, 14, I guess I should round appropriately, and 3,830 kilogram meters per second. Okay, double check, make sure that lines up with my expectation. So I expected both of those numbers to be positive. Nice. And also I noticed that it has more of a y component than an x component, which makes sense for a 50-degree angle. So I trust this. All right, P2. The momentum of the second asteroid in this inelastic collision, the initial momentum of it is, okay, so the magnitude is 18,000. So I can find the vector form of this, the component form of this, by 18,000 cosine of 65, comma 18,000 sine of 65, and I get out as a result 7,607 and 16,314. Okay, so let's check my intuition there. So I have two values. Whoops, one of them is supposed to be negative, right? So I've got a leftward pointing vector and up. So up means a positive vertical component. That's the y component here. Left should mean a negative x component. So I get a negative here, negative here. So this should have been negative in the first place. Now, why is this? In the last video, I mentioned that if we measure from the vertical axis, then I switch my sine and cosine in terms of my component, component decompositions. If I measure from like the negative side of the x-axis, like here compared to the start of my vector, I'm on the left side, the negative side of the x-axis, that value will give me a flipped, like if I use this version of the angle, this measured from the negative side of the x-axis, I'm going to have to append that negative sign to my x component. So I recommend just double checking your intuition at the end every time. If that really grinds your gears and you don't want to have to think about signs, then my solution for you is to always measure everything from the positive x-axis. So like if I were to measure this angle as 115, oops, yeah, there we go, 115. Then I would just get out that negative sign for free. And I wouldn't have to think about the sign at all. I could just leave 18,000 as positive. Okay, but again, like I recommend intuitively just kind of like looking at it and saying, okay, what should the component's signs be? Okay, negative in the x direction, positive in the y direction. Cool. So I trust that. If I were to draw this as a momentum chart, I could. Let's do that. I'll have that P initial plus delta P equals P final. Sweet. The initial momentum for the first asteroid, 1, 2, and total, points up and to the right. It has a value of basically 3214, 3830, which I'll represent as this little vector. Okay, now the second asteroid has a momentum of negative 7607, 16314, which is pretty big. So I'm going to draw it like this. Boom. So my total initial momentum for my system is just going to be the sum of these, and they just add component-wise. So that's going to give me 4393 negative, there we go, negative 4393, and 20,000, 20144. Cool. And that's a vector that largely points up and a little bit to the left. Something like that. Boom. Okay. Now, I can think about the fact that this is a closed system. There's no external forces acting on the system. For that reason, there's going to be no change in momentum in the total. 0. However, the individual elements of the system, the subsystem components, are allowed to change momentum. And in fact, they will, right? They're interacting with one another. So they're each putting a force on one another. Now here's the clever trick. So if they stick together, the final velocity of the first asteroid is going to be the same as the final velocity of the second asteroid. So at the end, after they've stuck together, they're going to be traveling at the same speed. So I know that since the total momentum is conserved, I've got the two masses traveling together as if they're one mass traveling at the same speed. So I can find the speeds of the two masses traveling together. So let's do that. P final is just the mass total times the velocity final, which is going to be, what did I say, 15,000 and 5,000? Yeah, 18,000 and 5,000. No. 500 and 1,500 kilograms makes 500 plus 1,500 kilograms makes 2,000 times whatever the final velocity is. And these are vectors. So that's 2,000 times VF vector. So the final velocities of these two meteors, these two asteroids, can be found just by knowing that momentum is conserved, and at the end, when they're stuck together, they'll be traveling with the same speed. That's where this comes from. Cool. Okay, so we're pretty much ready. Let's just go ahead and solve for VF. So VF, the final velocity, is just going to be PF, the final momentum of the whole system, divided by 2,000, which is what? PF is the same as PI, total. This is total for both of these. Which is 1 over 2,000 times negative 4393, comma, 20144. Wow, handwriting's getting a bit sloppy, but that's from over here. There we go. All right, and when I run the numbers on that, I get negative 2.19. I'm just going to call it negative 2.2, comma, 10.1 meters per second. All right, sweet. So in the end, my asteroids have stuck together. Good. And they're traveling slightly to the left and upward at a rate of, they're kind of like a joined mass now, at a rate of 10 meters per second in the vertical direction and negative 2 meters per second in the horizontal direction. So the magnitude of this vector is going to be 2.2 squared plus 10.1 squared, square rooted, which is 10.33 meters per second. 10.33 meters per second. Nice. 33. All right, let me return briefly to my momentum chart here, just to have this thing totally filled out. So V final, these things are both just 10.33 meters per second, or in terms of their vector form, let's go ahead and do that. The vector form is just negative 2.2, 10.1 meters per second. Okay, cool. So now I can apply that to each of my individual masses and see what happened. The final momentum of my first mass is just going to be the first mass size times this final velocity. So it's going to be, how do I do this? I multiply 500 by the final velocity. So that 500 for the mass of the first asteroid. So 500 times negative 2.2 gives me negative 1100 for the x component, and 500 times 10.1 gives me 5050, 5050 for the y component. So that's a vector pointing in this direction. Same direction as the total vector, but a different magnitude. For the second asteroid, it's 1500. That'll give me negative 3300 here, and let's see, 15150 here. So it's going to be a vector that is 3 times larger and pointing in the same direction. Cool. All right. Last thing I can do if I want is find the change. So the change is just final minus initial. Let's do that. I get negative 4314, comma, negative 1220, which is a vector that points like, let's see, it's going to be going down, but mostly to the left. Nice. Something like that. Cool. And since the changes in momenta for this closed system must sum to 0, I know that the change in momentum for the second asteroid is the opposite. So positive 4314, comma, 1220. All right, sweet. It's possible that I made math errors, as always, but the elements of the first 2 rows should sum up to the third row, and the elements of the first 2 columns should sum up to the third column. It's kind of like this. There we go. All right. Adam from editing here. I realized one last thing I forgot to mention, which is that each of these vectors should sum up graphically too. So like here, in the middle row, here we go, the blue vector plus the shorter red vector should give me this last red vector. So I can kind of see, all right, the effect of this red vector on this blue vector is to bring it slightly over in the x direction and slightly up in the y direction. And hopefully that's reflected in this red vector on the far right. Similarly, in the upper row here, this initial vector plus this change in momentum, this change in that vector, give me a vector that's still pointing up, but less up and slightly to the left. So notice that in this case, what we found for the final velocity was magnitude 10.33 meters per second. That's in between the 10 meters per second and the 12 meters per second we saw initially. It can also be less than these, right? So like if I had these 2 things collide head on, it could just be straight up less than either of them. So if you imagine like two asteroids that each have 1 kilogram mass that have the same speed that come together and stick together, well, they had a total momentum of 0 to start. So their speed at the end would also be 0 after sticking together. So they coming together and kind of smush together, say, if they had the same initial momenta but in opposite directions. Okay, I think that's basically all I wanted to talk about in this video. Went through a pretty thorough example of how to use a momentum chart, and we also went through the clever trick involved with inelastic collisions, namely that the velocity of each of the individual members of the system is the same at the end, because they're stuck together, right? So if they had different velocities, they would separate. Cool. All right, I think that's it for now. I'll see you in the next one.